Welcome to the course MCDM techniques using R. So, in previous few lectures we have talked about elector, before that we have been able to cover AHP. So, now in this particular lecture we will start with another technique which is called TOPSIS. So, let us start. So, TOPSIS actually stands for technique of order preference similarity to the ideal solution. So, the kind of method that it is there is some indication in the title in the full form itself. In this particular technique TOPSIS in comparison to elector we require minimal number of inputs. So, subjective parameters that we require is typically criteria weights, and in some scenarios there could be other things as well. However, mainly it is criteria weights. If we compare it with the elector method, then there apart from the criteria weights, the decision makers were supposed to provide their inputs for different threshold parameters. So, if we compare with the complexity of elector that was there, the TOPSIS is quite a simple technique, a straightforward method. So, that will understand in more detail in the in this particular lecture. So, output is easy to understand. So, the way the whole procedure is done, the way the steps of TOPSIS are executed, the output that we see is quite straightforward, easy to understand, which was not the case with the elector. So, let us move forward. So, main idea behind TOPSIS is that best solution is the one which has the shortest distance from the ideal solution. So, as you would understand as we go along this lecture, that this particular method TOPSIS is a distance based method. We will see more those particular aspects in more detail later in this lecture. But the main idea is that we are looking for a solution, the best solution which has the shortest distance to the ideal solution and farthest distance from the anti ideal solution. So, we are we will be identifying the ideal solution and anti ideal solution, and our best solution among all the alternatives that are going to be there is going to be closest to the ideal solution and going to be farthest from the anti ideal solution. So, that being the main idea, and because of this kind of approach the TOPSIS is also referred as a reference reliable approach. So, let us understand this through a example and some graphs, some charts. So, let us take this example. So, we have two criteria to be maximized and they are having equivalent weights now, and we have two alternatives A and B. Now, we have to check their closeness with respect to the ideal and anti ideal solution. So, if we describe this particular example through a graphic, so you can see here we have two criterion, one along the x axis criterion 1 and the another one along the y axis, that is criterion 2. So, given these two criteria and two alternatives that we have. So, one alternative is this alternative A and the second one is alternative B. Now, to find out which one of these two alternatives, which one is the best one, we have to look we have to compute the distance of each of these alternatives from the ideal solution as well as the anti ideal solution. So, you see this is the point alternative A, and we have to see the distance from the ideal solution and then similarly for this one. So, similarly we have to see the distance of these two alternatives from the anti ideal solution. So, you can see from here. So, you would see that we are going to prefer the alternative which is going to be closer to the ideal solution. So, it seems to be alternative A just by looking at this particular graphic, just by visual inspection. We can see that the way these alternatives and everything else has been depicted, we can see that alternative is A is closer to the ideal solution and farthest from the anti ideal solution, while alternative B it is closer to anti ideal solution and a little further from ideal solution. So, this is how the whole TOPSIS method is all about. So, we will discuss other aspects of TOPSIS in more detail. So, there are 5 main computation steps that one has to perform to implement TOPSIS. So, first one is about performance scoring of alternatives on different criteria. So, we need to have those scores so that we can later on perform the other steps. So, performance scoring of alternatives with respect to each criteria. So, if we are doing ranking of cars and there are certain criteria that are being considered, for example price, for example efficiency, for example space. With respect to each of those criterion, we have to get the scoring of alternative with respect to each of those criterion. So, once that is there, then we can move forward. Then the next step is normalization of the performance scores. So, because these because these scores might have been taken, might have been measured on different criteria, which might be on different types of units. So, range of those scales could be very different. One could be in in kilometers, the another one could be in meters, and so different kinds of units can be used, and because of the numbers which are taken across those units could range from which could range from different low value to high value. So, therefore, to be able to compare the measures taken on different units, we need to perform the normalization. So, this is the second step that is to be done. Then once the normalization has been completed, then we do the weighing of the normalized scores. Now, as we talked about that one of the subjective input that we require in TOPSIS is the weights of the criteria. So, the decision makers, they are required to specify the criteria weights that they would like to use for TOPSIS modeling. So, using those criteria weights will we try to compute, we are going to compute the normalized scores, right, weighted normalized scores. So, that is third step where we compute the weighted normalized scores. Then in the fourth step, the distance computations from ideal and anti-ideal points are performed. So, each of the alternatives. So, if we have 3 alternatives. So, for each of those alternative 1, alternative 2 and alternative 3. So, we will take them one by one, and for the alternative 1 we will try to compute its distance from the ideal and anti-ideal solution. Then we will take the alternative 2 and perform the same process. So, these distance computations are to be performed for each of the alternative. Then once this is done, then we can go ahead and compute the closeness using some ratio based expressions formulas on the distance scores. So, once that this closeness ratio has been computed, then we can move ahead and do our ranking of alternatives. So, these are basic 5 steps. Now, underlying mathematics, how exactly these computations are actually performed. So, let us understand that particular aspect also. So, let us start with the step 1. So, step 1, we assume that we have information on these 3 things, just like other techniques AHP and elector that we have discussed before. We will be having alternatives. So, these in this case to explain the mathematics underlying TOPSIS, we will take alternatives as there are n alternatives. So, we are indicating that as A equal to 1 to n. So, there are n alternatives and there are m criterias. So, I indicating that range 1 to m. Then we should also have the decision matrix. So, that is being denoted using capital X, and the elements of this particular matrix is being denoted as a small x, AI. A is for alternatives which are going to be associated with rows, and then the I, which is indicating the criteria. So, this is going to be associated with the column side. So, on the rows side we are going to have the alternatives in the matrix, and on the column side we are going to have the criteria for in the decision matrix. So, alternatives are shown on n rows because we are considering n alternatives, and criteria are shown on m columns because we are considering m criteria. So, the rank is going to be n cross m. So, this is the information that we need to have to start with before we could actually apply TOPSIS modeling. So, as we talked about in the next step, that is normalization. So, there are different ways to perform the different procedures to perform the normalization steps. So, we will talk about a few of them. So, first one is distributive normalization. So, in this in this mode of normalization, what we do is the scores that we already have, the performance scores that we already have in the decision matrix, they are divided by the square root of the sum of each squared element in a column. So, column is representing the criteria. So, for each of the column, therefore, with respect to each of the criterion, we do certain computation. So, along one column, that is along one criterion, we will have the scores for each of those alternatives. So, all those elements, all those scores are going to be divided by the square root of sum of each squared elements. So, mathematically it is expressed in the slide also, as you can see, small r A I, A is standing for alternative, I is standing for criteria and row and column wise. So, R A I, that is the normalized score that we will get is equal to in the numerator part we have the actual score, actual performance score, that is small x A I, and in the denominator we have the square root of summation of squared element of all these scores along one particular column, that is one particular criterion. So, as you can see here in the denominator, under this denominator we have a square root, then summation is from a is equal to 1 to n, right. So, because we are having n alternatives. So, all the scores for all the alternatives, they are being summated, and the squares of those scores are actually being summated, and then a square root is taken. So, this is how we compute this distributive normalization, and this is going to be used later on in the next step number 3. Now, there is another way to perform this normalization. So, this is referred as ideal normalization. So, again there are two scenarios within ideal normalization. So, if the criterion is to be maximized, so we have talked about in previous techniques that there is typically going to be a preference direction for a particular criterion. So, whether the criterion is to be maximized or whether the criterion is to be minimized, right. So, for example, we talk about the ranking of car, right. So, efficiency is something that we would like to maximize, right, but price of the car is something that we would like to minimize. So, a different criterion might have different preference direction. So, considering that our computation in this ideal normalization is going to be different. So, if the criterion is to be maximized, then the scores are divided by the highest value in each column, that is with respect to each criterion. So, in this case the normalized score RAI is going to be equal to, in the numerator side, XAI divided by maximum of XAI, where A is 1 to n. So, out of n alternatives along a particular column, we have to see the highest, we have to pick the highest value, and that highest value is going to be used as the denominator. So, and then we will get this ratio, which is going to be used as this normalized score. Similarly, in the other scenario, if the criterion is to be minimized, then what we do is we do the scores are divided by the lowest value in each column. So, in each column, that is with respect to each criterion, we take all n alternatives, and each of each of these scores with respect to belonging to each alternative, they are divided by the minimum value out of all those n scores. So, as you can see here in the mathematical expression here, that normalized score small RAI is being equal to XAI in the numerator, and then divided by the minimum value of XAI, where A is 1 to n. So, in this fashion ideal normalization can be performed. So, we talked about two types of normalization procedure. One, we talked about distributive normalization, where a square root of square root of a summation of squared elements is done, and in the ideal normalization where we divide by either the maximum score or the minimum score depending on the preference direction of the criterion. So, there are other types of normalization procedures as well, so that you can refer in your own time. So, these are the two popular ones which are typically used. However, at this point I would like to tell you that the theory part that we are discussing here in the slides, and the way we talked about the how the normalization is done, what is the exact expression, mathematical expression that can be used to compute the normalized scores. However, the way normalization is going to be implemented in R, and the functions and the packages that are going to be available to us could be slightly different. So, that depends on the author who has actually written those functions and the normalization procedure that they might have implemented there. So, there there could be slight variations of what we are discussing here. So, now we move to step number 3. So, in this particular step so previous step we have already computed the normalized scores. Now, in this step we are going to compute the weighted normalized scores. So, at the end of this step we will get the weighted normalized decision matrix. So, we have the criteria weights Wi, so that are to be provided by the decision makers as subjective inputs for this particular model, TOPSIS model, and then normalized scores RAI that we have already computed. So, weighted scores are nothing but simple multiplication of these two values. So, criteria weights are going to be multiplied by these normalized scores. So, VAI, so that is the weighted normalized score, is going to be WI multiplied with RAI. So, we will get the weighted normalized score. So, let us move forward. Now, we come to the step 4. So, there are a few more details in this particular step. So, what we do in this step is that distance computations from ideal and anti-ideal points. So, that is done. So, main computation that we do is actually part of this particular step. So, in this step weighted scores obtained in the previous step are used. So, weighted normalized scores we have already obtained in the step 3. Now, we are going to compare each alternative having these weighted normalized scores with the virtual ideal alternative. So, there is no real ideal alternative. So, we are going to define a virtual ideal alternative. Similarly, we are going to define a virtual anti-ideal alternative, and each of the alternative that we have and the weighted normalized score that we have, those scores are going to be used to compare the alternatives with these virtual ideal alternative and virtual anti-ideal alternative. So, how do we define these virtual alternatives? So, we are going to cover 3 ways which can be used to define these virtual alternatives. So, let us talk about the first method. So, in first method constructing a virtual ideal alternative would be like this. So, coordinates can be expressed in this form. So, V1, and you can see a superscript as B that is standing for the best value, similarly V2B and up to VNB. So, given the given the n alternatives that we have, right. So, we are going to pick the best value given the given the criteria that we might have. We are going to pick the best value along all those criteria. So, you can see here using best scores on each criterion. So, again there could be 2 scenarios. So, that is max A, right. So, A is for alternatives. So, alternatives 1 to n. So, max A, so we are assuming that there are n alternatives. So, A ranging from 1 to n, and the max A of VAI. So, V which we have already computed is the weighted normalized scores. So, if criterion I, so this is for the criterion I, if criterion I is to be maximized, then we will take the max value. Similarly, if the criterion I is to be minimized, then we will take the minimum value, that. So, that value is going to be minimum of A VAI. So, among all the alternatives, so among all the scores for each of these alternatives, and with respect to a particular criterion. So, if we just look at one particular column, so that would correspond to one particular criterion. So, for that criterion we will see which alternative is going to be is having the maximum value or minimum value. So, if the criterion is to be maximized, then we will pick the maximum value. If the criterion is to be minimized, then we will pick the minimum value. So, once this is done, then we use these best scores on each criterion to construct our virtual ideal alternative. So, remember, if the criterion is to be maximized, the best score is going to be the highest value. If the criterion is to be minimized, if the criterion is is to be minimized, then the best score is going to be the minimum value. So, therefore, that has to be taken care of while constructing virtual ideal alternative. So, once this is done, then we will get this virtual ideal alternative denoted as V1b, V2b up to Vn V. Similarly, to construct virtual anti-ideal alternative, we have to pick the worst value. So, again two scenarios. If the criterion I is to be maximized, and since we are picking the worst value, so we will take the minimum value. And in the second scenario, if criterion I is to be minimized, then since we are looking for the best value, we will take the maximum value. So, it is just reverse of what we did in the construction of virtual ideal alternative. So, in the virtual anti-ideal alternative, we will take the worst scores, and therefore, we are denoting this virtual anti-ideal alternative as V1w and V2w up to Vnw. So, now let us move forward. So, that was one way to actually define the virtual alternatives. Then there could be other ways to define these alternatives. For example, one approach could be not considering these given alternatives and the values and the scores that are there for each of those alternatives. Rather take a absolute position wherein absolute ideal and absolute anti-ideal points are defined. So, in this case, because later on as we will see that the values that we compute is actually they are going to lie between 0 and 1. So, why not take ideal point as 1 1 1 and the anti-ideal point as a 0 0 0. So, irrespective of the actual values of the alternatives, will have the absolute ideal point and will have the absolute anti-ideal point, and any alternatives that we might have, they can actually be compared with these absolute ideal and absolute anti-ideal points. So, this is another way to define virtual alternatives. Then what could be the third way? So, in the third way as we talked about that criteria weights are anyway they are required to be specified as subjective inputs from decision makers. Similarly, for the virtual alternatives also we can take them from the decision maker as subjective inputs. However, we have to take care that these numbers that we take from decision maker, they should lie within the range which are to be computed by the previous methods. So, if you see the range is typically going to be 0 and 1. So, in that sense these input provided by decision makers, they should actually be lying in this particular range. So, let us move forward. So, in this step 4 we talked about distance computations from ideal and anti-ideal points. So, till now what we have talked about is how to define these ideal and anti-ideal points. We talked about 3 ways. Now once we know these ideal and anti-ideal points, we already have the information on the alternatives. So now we can go ahead and calculate the distance for each of these alternatives, and between each of these alternatives and the ideal and anti-ideal points. So how do we compute the distance? What is the metric that should be used to perform the this computation? So the most popular distance metric that is typically used is the Euclidean distance metric. There are other distance metrics, for example Manhattan distance, this is also used. So because Euclidean distance being more popular, so we will talk about this. So how do we use Euclidean distance to compute the distance between alternatives and ideal and anti-ideal points? So you can look at this expression here in the slide. So small d, and in the subscript a, that is for alternatives, that is 1 to m, and then ideal. So we are trying to compute the distance from the ideal point. So this is nothing but a square root of then summation from I to from summation over on I, where I is from 1 to n, given that n alternatives that we have. And then within parentheses we are having VIB minus VAI and the square of that. So this is very typical of Euclidean distance formula, where you might remember that it is typically x1 x1 minus x2 square plus y1 minus y2 square and a square root of all this. So similarly this here also the similar kind of expression has been used here. So with respect to ideal and anti-ideal point, so we can use these two expressions. So for the anti-ideal point, this is the expression d a anti is going to be computed using this part, a square root of summation on I, in parenthesis we have VIW minus VAI square. So using these two expressions we can always compute the distance of each alternative from ideal and anti-ideal points. So let us move forward. So now at the end of step 4 we will have the distances from all the alternatives, between all the alternatives and ideal and anti-ideal points. So once that is there, we can go ahead and compute the closeness ratio for each alternative. So how do we do this? So you can see an expression written in the slide. So this closeness ratio, that is capital C A, is going to be computed for each of the alternatives. So this is C A equal to, in the numerator, D A anti. So we in the numerator we take keep the distance that was computed with respect to anti-ideal point, and in the denominator the summation of both the distances, that is distance from the ideal point and distance from the anti-ideal point. So you see here that given that we would like to pick the best alternatives based on what we talked about, that it is going to be closer to ideal point and it is going to be farthest from anti-ideal point. So if a alternative which is going to be the best alternative, if it is closer to the ideal point, so therefore this distance DA ideal is going to have a small value, right. So because of this, the DA ideal is going to be smaller value. So once we keep in denominator and compute this ratio, so this for this best alternative, this CA value is going to be closer to 1, right, and the worst alternative, this value is going to be closer to 0, because distance from the ideal point is going to be on the higher side, and therefore the denominator value would be on the higher side, and therefore the overall value of closeness ratio will be closer to 0. So this closeness ratio CA, the value is going to lie between 0 and 1, as you can see from the expression itself, where as I talked about, a value approaching 1 indicates the preferred alternative. So for the preferred alternative, this value is going to be closer to 1. So for each of the alternatives we are going to compute this closeness ratio, and once we have these values, for closeness ratio for each alternative, then we can easily see which one is the best preferred, and we can also produce a ranking, right. So, these are the 5 steps that we are supposed to perform to complete our to do our TOPSIS modeling. So, what we will do now is we will do an exercise in R to actually understand whatever we have discussed till now. So, the steps that we talked about, 5 important steps. First step was about getting all the information that we have, the alternatives, the criteria and the performance table. Then the second step was about doing normalization. So, the scores are to be normalized, because we would like to compare the performance on each alternative. So, after that normalization we talked about the weighted normalization scores, because different criteria might have different weights given the preferences of decision maker. So, that is to be incorporated in the procedure itself. So, that is done in step number 3. Then in the step 4 we define the ideal and anti-ideal point, and once that is done we perform do the computation for each alternative. So, we do distance computation for each alternative with the ideal and anti-ideal points. So, given that in the 5th step we actually compute the closeness ratio. So, now in our studio we will take this example ranking of cars, and we are going to have 3 alternatives and 4 criteria. So, we'll in this lecture we will like to stop here, and in the next lecture we will do our exercise in R studio. Thank you.